Hey team, today we are going to look at rectangular hyperbolas. They are a type of graph or function that we're going to look at. They are based off this equation here, y equals 1 on x. We'll look at why the shape of it is the way it is because of that equation. We'll then go into some basic facts about hyperbolas and the fact that they have some asymptotes. We'll look at the general form of it, and we'll do a bunch of sketching of a bunch of different variations of it, so we really get our sketching skills down pat. So let's jump straight in. We have the equation y equals 1 on x. What I want you to do is you'll pause the video in a second and fill out this table just to practice your fraction skills. And then after you have done that, come back and check if your answers match mine. So pause now. Rightio, so hopefully you've had a go at doing your fractions. So they are 1 on -4, 1 on -2, this just becomes -1. This will become, let's do it here, y is equal to 1 on -half. If we ever dividing by a fraction, we can just multiply by the reciprocal, so this is going to become 1 times by -2 on 1, which becomes -2, so we get -2, and this pattern stays the same. 4, 2, 1, half, 1/4. So there's our values. Now, keep these in mind. If you don't have these written down, just write them, scribble them down in a table really quickly, because they're going to be really important for questions that we have on the next slide. Oh, we're going to plot these first, sorry, then we'll have a think about them. So, a quarter is 4, so about there. Let's use a different color. About there. 2 is half, 1 is 1, 2 is half, and 4 is a quarter. So we get those values, and then we get very similar looking over here. Like that. And if we play connect the dot, we get this lovely shape here. Which is now a rectangular hyperbola. Now, let's actually ask some of those questions. If we continue to plot these points in the positive x direction, so we've got this sort of shape going on here. If we kept going this way, what would the graph approach, and will it ever touch that value? Okay. So have a look. What are we getting closer to in our y values as we keep coming this way? What are our y values getting closer to? Hopefully you might notice they are getting closer to y equals 0. Now, will they ever touch that? Can we ever get a value of y equals 0 for this function 1 on x? Well, if we put a 60 in here, we're going to get 1 on 60. If we put even x equals 1,000,000, we're going to get 1 on 1,000,000. But it doesn't matter how big of an x value we choose, our y value still has some size. Now, it is getting incredibly small, infinitesimally small, but it doesn't actually become 0. So the question to this, we are getting closer to y equals 0, but no, it will never touch. Now, the same thing can be asked for as our x-coordinates keep getting smaller, or I should say as they approach 0, as x approaches 0, so x equals half, quarter, 1/8, 1/16, what will our graph approach? Well, let's come back. Now we're asking, as we get closer and closer to x equals 0, what is our graph doing? And it appears it is heading up really high. So same thing, we can interpret some more values in here and think about what happens. Well, if x equals 1 on 8th, y is going to be 8. If x is equal to 1 on 16th, same. We put 1 on 1,000,000 in there. Okay, y will equal 1,000,000. So our value, okay, our y values are actually approaching infinity. As we get closer and closer, like we did 1 on 1,000,000,000. Well, y is 1,000,000,000. We're getting really, really close. The next question as part of this though, what happens when x equals 0? Come back here, what happens at x equals 0? Okay, if we put it 0 in, well, we get 1 on 0, which is undefined. Okay, it doesn't have a solution. We don't actually have a value. So this gives us some key important facts about our graph here. As we're going along our x-axis to the positive direction, we get closer and closer and closer, but never touch it. And same here, as we come back this way, we get closer and closer to the y-axis, but we can never actually have a y-axis intercept in this basic form because we can't have divide by 0. We can't let x equals 0. The function becomes undefined. So what does that mean for these sort of special points? These are what we call asymptotes. Asymptotes are points where the function gets really close to, but never actually touches. And we draw them as dashed lines. Okay, so these are asymptotes. So what's the equations of them? So the visual lines this graph will never touch. What's the equation? Well, this vertical one here, hopefully that's pretty straightforward. That's x equals 0. Okay, we can never have x equals 0, that's fine. What about the horizontal asymptote though? This one going across, that one is actually y equals 0 because we can never get it. Our asymptote equations are effectively telling us what are the values that we can never achieve with this function. Well, in this case, we can never get x equals 0 and we can never get y equals 0. So x equals 0 and y equals 0. And why is it called a rectangular hyperbola? Well, it's called rectangular hyperbola because these two asymptotes are at right angles to each other. We can get, but we don't look at in year 11 and 12 methods, we can make hyperbolas that if we draw the Cartesian plane, the asymptotes might actually be something like this, and the graph is there, and the asymptotes aren't at, so the red's the asymptotes, and the graph is the blue bit. Okay, we can have non-right angle asymptotes, but we're not going to deal with that at all in our course. We're only dealing with rectangular hyperbolas where our asymptotes are always at right angles. So here's our basic shape. What we need to make sure we do, unless we have a domain, is we must include our arrows on the end of the graph, because if we don't have a domain, the function continues on non forever. So we must have those to indicate that that is occurring. In the basic form, it goes through 1, 1 and -1, -1. And we have asymptotes at x equals 0 and y equals 0. Like I said, we normally draw those in as ruled dashed straight lines. Now, I can't use a rule here on PowerPoint, but that's the basic shape. Because there's no intercepts of this basic form, you need what are called points of reference when graphing, and we need 2 of them. Now, points of reference are just a coordinate on each of the lines. These help us give shape and size to the graphs. Okay, in this case, we've used 1, 1, and -1, -1. And this will be pretty similar for most of the graphs we're going to look at, unless one of the x values falls on an asymptote, is use x equals 1 and x equals -1. They're your 2 easiest values generally to substitute in and get your points of reference if you don't have intercepts. But as soon as we start translating this, we'll have intercepts, and we'll talk about that when we get to it. Okay, so the general equation, okay, is y equals 1 on x, or really we can actually think of it of y equals a on x, where a is our dilation factor. Okay, what you need to think of is what happens instead if this a was 3. Okay, so if we had a 3, if we put 1 in for x, well, our y value becomes 3. So our graph, if we put 1 in x, y, if we put 1 in for x, our y value would become 3, and that actually means that it's way up there. And our graph is, I guess, what we could consider fatter or dilated out. Okay, it's wider and further away from the origin. So if our A value is larger than 1, those curves are further away from the origin. What we need to be careful of, though, is sometimes when we have variations like this, where 3 is in front of the x. Technically, we want to get used to thinking of the form A in the numerator, which in this case, we can see here that 1 on 3 of x is the same as 1/3 by times by 1 on x, which can also be written as 1/3 all over x. In this case, we can see now our numerator value, okay, A is equal to 1/3. So for this graph, let's use green. When x is 1, y is only 1/3. And so it comes in really close to the origin. Okay, it's dilated inwards, makes it really compressed. So just be really careful if you're asked what the dilation factor is. By convention, it's if we could write that coefficient in the numerator, that's what your dilation factor is. It's not super important, though, that you know this, because the methods we're going to use for sketching, unlike sort of quadratics, the dilation factor is sort of irrelevant to our method of sketching, because we're just going to use substituting some points and pay more attention to the asymptotes. The dilation factor comes out in the wash of the shape of your graph when you do your points of references anyway. So here, as you can see, 2 on x is the solid red line. It's further away from the origin. 1 on 3x is very close to the origin. Okay, so the smaller the dilation factor, the closer it'll get to the origin. Rightio. Like quadratics, cubics, any of the polynomials, we can apply transformations, we can translate, we can dilate, we can reflect. Is there any that I'm missing? No. Okay. In this case, and we'll come to it at the very end, but our general form is this. No, what am I doing? Okay, this is our general form of the hyperbolic equation. Okay, A is our dilation. Okay, and also we can have reflections if that's made negative, or the x itself here is made negative. That would be reflection. H is just like with quadratics and cubics. That's our horizontal translation. And as well with the K, that's our translation as well. So we're looking to recognize those when we're looking for transformation. Dilation up top, if the reflections would be the whole equation is made negative, or the x itself is made negative, and then our two translations. But again, we're more focusing on graphing at the moment by recognizing where are the asymptotes going to be, and then that in turn tells us what our translations are. Okay. So really quickly, if there's a negative in front, okay, the graph is effectively being reflected through the x-axis, so it's being essentially flipped about that. What was up here is now down there, and what was down in this quadrant is now up in that quadrant. What's special about hyperbolas is that reflecting about the x-axis like that would actually give us the same graph as reflecting about the y-axis. We can get the same thing when it gets flipped that way. So we actually get the same result. And you can play with that. If you wanted to graph y equals -1 on x versus y equals 1 on -x, okay, reflecting about either the x-axis or the y-axis, you'll see that both of those look identical. Okay, so sketch below the graphs of y equals 3 on x and y equals -2 on x. The first thing to recognize is there's no translation. Okay, we can tell there's nothing else apart from x in the denominator, and there's nothing else added on at the end of the equation either. Okay, so that means our asymptotes for both these functions are going to be at x equals 0 and y equals 0. And with asymptotes, you must write them, draw them in and label them with an equation. You can't just put the dashed lines and then not actually state what they are. From here, what you want to do is, because the asymptotes are on the axis, we have no intercepts. So normally, okay, steps is 1, we do asymptotes. Okay, 2, we do intercepts if they exist. Okay. And then from there is point of reference. Okay. In this case, we've got no intercept, so we must do point of reference. Like I said, it's probably best to do x equals 1 and x equals -1. So let's do x equals 1 for, we're going to focus on this first equation, which is 3 on x. So we're going to get y equals 3 on 1, which is y equals 3. And same, we get y equals 3 on -1. Y equals -3. So let's graph those in. There and there. We want to label them in coordinate form. So 1, 3, -1, -3, and then we put in our shape, and we must draw our arrows going away. Common mistake people make with the shape of their graph is they'll do something like this. It's got a nice curve to it. It's coming around down here. That's really well. But up here, that's a big no-no. That's a really big no-no, because our line is going away from the asymptote, which doesn't happen mathematically. Our line gets closer and closer and closer to the asymptote, but never touches. Year 12, you got to pick your examiner and you're asked to graph a hyperbola, which does come up. You'll lose a mark there for shape, because that shape is not representative of what the actual equation does. So we want something like that, going clearly towards the asymptote with arrows on the end, and same here. There we go. So that's first equation. We can do the same with the next one. We'll use x equals 1 and x equals -1 again. Let's do this in green. We get -2 on 1 is -2. -2 on -1 is 2. Okay, so when x is -1, y is 2. -2. Same thing. Graphing in. Graphing in, arrows on the end, and there we go. That's all that's required. So at no point did I actually need to think about the dilation factor. By just having points of reference and then drawing my line through it, that covers the concerns about dilation factors. Now we're going to try something with the translation in. And I gave you the general form before, and you might recognize, okay, that's my horizontal translation. But let's think about it from a mathematical point of view to prove why that is a horizontal translation. We said way back here, okay, our vertical asymptote is at x equals 0 because our function is undefined at x equals 0, because we can't divide by 0. Now, in this case, our denominator is different. Our function will still be undefined when the denominator is equal to 0. So in this case, though, because the -1 is there, that's not going to happen at x equals 0. It's going to happen at some other value. So you can always find this asymptote, even if you forget the general form of a hyperbola and what's going on. You can always still solve it by going, well, the asymptote has to exist when the denominator equals 0. So we can just let the denominator equal 0. So let the denominator equals 0, so we get x minus 1 is 0. That's when it's undefined. which is going to occur when x, in this case, x is 1. The minus 1 there, when it's brought over as an inverse operation, becomes positive. That's why that sign flips when we read off our translation. Looking here, okay, it's x minus 1, but our horizontal translation is positive 1. So we can put this in as our vertical asymptote, x equals 1, and we also have a horizontal asymptote, which, because it's not translated up, is still y equals 0. Rightio. What we want to look at next, okay, is the general shape and idea of it. Is it reflected at all? Because this is going to impact, as you might now notice, our asymptote is not on the y-axis. That means our graph might be coming through here or might be coming through here, but that means we have an intercept, which is really important because we want to label them. Okay, if an intercept exists, we do want to always label them unless the question tells us to explicitly not to. In this, and a point of reference where appropriate, and we are told to actually label intercepts. So back to what I was talking about, the shape. There's no reflections, so within our asymptotes it looks like this. So we're going to have something here and something there. So this is where our intercept is. So the reason why I'm going over this is a great way to check your maths is I'm going to expect a negative y value for this intercept. If I get something positive up here, then I have an issue. That's not what we expect from the shape. So let's go quickly and find that. So we're going to let x equal 0. So we get y is equal to 2 on 0 minus 1 is 2 on negative 1, which is negative 2. So there's that point there. So we have 0, neg 2. And what I'm going to do now, I can't pick x equals 1 to find my other point of reference because that's on the asymptote. So I'm going to just come across one more spot, and that's at x equals 2. So we get y is equal to 2 on 2 minus 1. 2 on 1 is equal to 2. So we get that point there. 2, 2, and draw in a line with our arrows. There we go, graph done. Let's combine it now with, we also have a minus 1 here. So that is going to be, if we think about whenever we have an equation, let's even think of a polynomial, x cubed plus x squared minus 2x or something like that. That's our sort of polynomial. And then as soon as we do a plus or minus a constant at the end, whatever value, y value getting out of this whole bit, all that's doing is adding or subtracting a certain amount, which is effectively changing the y value by whatever the c amount is. So it moves the graph up or down. That's why it's always, whatever that constant is at the end, that's always why it is a vertical translation. So if we go back to what our steps were, let's identify what our asymptotes are. I want my eraser. There we go. So same thing, to double check, the appropriate way to do this is let the denominator equal 0. So let the denom equal 0. So we get x minus 1 is 0. So we get x equals 1. So that's our vertical asymptote, which happens to be the same as the last one. And then we need to recognize, well, our graph, that's a translation. Okay. So our other asymptote is that y equals negative 1. So let's put that in. Y equals negative 1. Okay. Now we want to look at our shape. Okay. Because we need to think about, do intercepts exist? Well, our shape between the asymptotes has to be here and has to be here. So same thing, we have this intercept here, but we also now have an x-axis intercept. So we're going to have to find both intercepts. So let's do y-axis one first, because that's always the nice easy one. We let x equals 0. So we're going to get y is equal to 2 on 0 minus 1 minus 1, 2 on negative 1 minus 1, negative 3. So, that's not what I wanted. Our first intercept will be here. 0, negative 3. And now we can do our x-intercept. So we have to let y equals 0 in this case. So 0 equals 2 on x minus 1 minus 1. No, 1 is equal to 2 on x minus 1. Now, because our x is in the denominator, we need to bring that whole denominator across. So our inverse operation step here, the next step is to multiply by x minus 1. And the same over this side, multiply by x minus 1. So we end up with x minus 1 is equal to 2, and we get x is equal to 3. Let's fix this up. So there's our other intercept, 3, 0. And you'll notice both of these is like negative 3 and 3. That's not always the case. It's just a fluke with this function. But we can come in and draw our shape. Okay, making sure our line is going towards the asymptote and through our intercepts. I'll leave this one for you to have a go at, but it's got a reflection. The same thing still applies. Okay, just need to think about the fact that the graph is reflected. So it was normally like this. It's going to be reflected about, so shape like that. So that's going to impact where you're trying to calculate your intercepts and what you should use as a logic check. Okay, my intercepts here met what I expected logically due to the shape. But you can have a go there. So it brings us to our general form. Y equals a on x minus h plus k. H is our horizontal translation, it impacts the asymptote. K is our vertical translation, it impacts an asymptote. And then a acts as a dilation factor. We don't have to stress too much about that, because when we find our intercepts or our points of reference, it comes out in the wash. We don't need to worry too much about the shape. The only time that's really important is, like in this case, when we have a negative value there, means the graph is being reflected. We don't need to worry about that next slide that flashed up. The only other thing I want to state here, it asked us, and points of reference where appropriate. Do I need one? No, because in both parts of the hyperbola, on both my lines that make it up, I already have a coordinate that explicitly states where it's going, so I don't need any other points of reference. Here, I did need a point of reference because there was no intercept on this side, and in this case, I needed 2 points of reference because there was no intercepts at all. So that's how we know whether we have, if we have an intercept, use it. If not, then you need a point of reference on that line. If you have any questions, as always, stick them in the comments below or on Google Classroom. Thanks, and see ya.